Aquí, se encuentran aquí en la universidad, aquí visitándonos en el Instituto de Ingeniería, y dentro de nuestro proyecto que es validación de productos de reanálisis de la precipitación para la modelación lluvia escurrimiento en México. Él nos va a hacer la presentación, Information Extension for Precipitation in Space and Time. El doctor Hannes es líder del equipo científico de hidrología de superficie en el Instituto Leipzig de Ingeniería Hidráulica y Recursos Hídricos del Departamento de Hidrología, Gestión y Protección del Agua de la Universidad Técnica de Braunschweig, Alemania. Entre el 2018 y 2020 fue investigador en el Instituto de Ingeniería Hidráulica y Gestión de Recursos Hídricos en la Universidad Tecnológica de Viena, y entre 2016 y 2018 fue investigador asociado en el Instituto de Hidrología y Gestión de Recursos Hídricos en Leibniz, en la Universidad de Hannover, en Hannover, Alemania, y ha tenido algunos reconocimientos y apoyos en participaciones de diversos proyectos, así como también cuenta con numerosas publicaciones. Y también ha estado a cargo de cursos y también ya ha dado asesoría a distintos estudiantes en el área que maneja. Entonces, sin más preámbulo, le cedo la palabra al doctor Hannes Müller. Thank you. Welcome.
Thank you for the nice introduction. My Spanish is not so good, so I will do the presentation in English. Welcome everybody to my talk, and first of all, thank you for that opportunity to speak here, that we can be here in Mexico. This is the first time for me and my colleagues here in Mexico, and we really enjoyed the time that we had so far, and we are really looking forward to the days that are coming. Speaking of my colleagues, we are sitting here in the first row. This is Christina Radke, our expert for water quality and isotopes. We have Henning Müller, expert for coastal water management and artificial intelligence applications in hydrology, and Tobias Langmann, our expert for groundwater and hydrogeology. The presentation today is split in two major parts. In the first part A, I want to talk about scientific activities at HYDRIF, just to introduce our institute a bit and that you get an idea of what kind of research we are doing and about the range of projects that we have. And in the second part, I want to jump into a more scientific part about the extension of precipitation information in space and time. I've got like 45 minutes for this talk, and I would be super happy if this is not a monologue. So you see that we have really different chapters with A and B. So if you have any questions in between, feel free to ask them immediately. Don't hesitate. However, we will also have at the end some time for questions. So let's start with the first point, the scientific activities at HYDRIF. Our institute is called the Leichtweiß Institute for Hydraulic Engineering and Water Resources. And based on the structure of our university, it's located at the Faculty of Architecture, Civil Engineering and Environmental Sciences. The Leichtweiß Institute consists in total of 4 different departments. Our department is Hydrology and River Basin Management, led by our professor Kai Schröter. If I go back to the slide with the images, this is Kai, professor at our department now since 2 years. The other departments are Waste and Resource Management, Hydromechanics, Coastal and Ocean Engineering, and Hydraulic Engineering and River Morphology. So although it's called department and not institute, the 4 departments that you can see here, we act all very independently, so it's more or less like having smaller institutes combined to a bigger one. Regarding the research that we have at our institute, the general focus is on analysis, monitoring and modeling of the hydrological process in its holistic way. And based on the federal country where we are located, we are focusing on low mountains, lowland regions, and also on coastal areas. we don't have a classical structure like one team is focusing on groundwater, another one only on water quality, another one only on surface hydrology. We try to create our projects in a way that they are really interdisciplinary. So that makes it a little bit more tricky to classify the projects that we have, but we came up with a classification that we think applies quite nice. The first class of projects are integrated modeling systems for river basin management, and in that first group, we also analyzed the impacts of climate changes, land uses changes, and demographic developments. The second class deals with forecasting and warning systems for floods, low water and water pollution. Third group with simulation models, because we most of the time we don't have all the measures that we need. And for impact studies, we want to know how different measures or climate change or different developments will impact the water cycle, and hence we needed simulation models. Last but not least group, system-oriented monitoring. To get rid of this data scarcity that we have, we are installing a lot of sensors to have a better idea how the flows work in our catchments and institutes. And despite the conservative measurement devices, we have also so-called new data sources. So we have citizen sciences and opportunistic sensors to gain more information. On the next slides, I have some project summaries to give you always a brief idea of the project, and I will spend a few words on each project. So for the first class about these integrated modeling systems, I want to show our directed project. It's funded by the EU, which means it's a really big project with numerous institutes and other institutions involved. And the idea of the disaster directed project is to increase the disaster resilience during extreme events. So what often happens is extreme events happen not that often. That means most institutes and agencies don't have too many experience how to interact with each other during such an event. And that leads to the fact that each institute or agency or the fire workers, they act more like silos, so independent from each other. Maybe you have one short exchange in the morning, what was done from one group and the other one. And the idea of the directed project is to build an open source software where all of these different institutes can interact with each other, that you can upload data in real time, you can gain new information, you can see what the other did so far. And for that, very important is to involve the stakeholders, to see if that really works for them, and if it's also applicable in the real world and not just a dream from our university. And to guarantee that stakeholder inclusion, we have here some real-world labs in Europe. We have 2 or 3 real-world labs where we also train some extreme events and see how people interact and work with each other. Second project is the UWMS project, and that one is dealing with water quality. So our colleague Christina Radke is working in that. It's located in the capital of Germany, in Berlin, and we have a couple of lakes there, and the water quality of that lakes is not too good. We have here 2 main steps or 3 main steps. The first one is the monitoring, so that we know how bad is the water quality actually. So we have regular monitoring devices installed there, and we want to see how we can improve this water quality by different measures. And because we cannot always apply a measure and see if it works or not when taking the measure away, trying the next one, we have to model the impacts, and therefore we're using the SQL-W2 water quality model for the whole chain of lakes. And this is our integrated approach to determine the impact of the measures and then giving a recommendation of how the water quality can be improved. Coming to the second class of projects that we have, the forecasting and warning systems, here shown for a project in the coastal area. So this is one of the projects where Henning is working in. We have a lot of water coming from the inland that has to be drained to the sea. In our case, it's the North Sea. And the way that this drainage management here is operated within the last years or decades is always based only on the expertises of the people working there. And these expertises cannot cover the upcoming changes that we have by climate changes and also the different flood risks that we have. So we try to face these challenges and to improve the water management that we have here, because this drainage of the non-salty water to the sea is always also a loss of water. For this project, we want to apply here artificial intelligence models, here shown a neural network in its form of an LSTM model, and the outcome of that improved management would be better management of the flood risk in the inland and also its water resources. And we have also other effects, like we want to increase the efficiency of the pump costs, and we want to use renewable energies. Third group of projects is we don't have an abbreviation for that. It's about the groundwater in Brunswick. So what you can see here is Brunswick, the town where our university is located. We have in total 250,000 inhabitants, which is maybe a bigger district in Mexico City. But nevertheless, we have urbanization and we have more people coming to Braunschweig, which increases the pressure on the local water cycle. And one of our main sources that we have or that we can take water from is groundwater. And before we want to take this groundwater, we want to see the effects. And for that, we need to understand how the groundwater works. And to understand the groundwater, you need to understand the hydrogeology. And what you can see here, this detailed map, we did not have this some months before. This is all the work done by Tobias. So Tobias went to the archives, to the different borehole informations gained over the last decades, built that very, very detailed 3D model of the hydrogeology of Brunswick, and is translating that one now into a groundwater model. And with that and the additional measurements that we have from our isotopes, we know where the groundwater is flowing, under which circumstances and under which boundary conditions. And with that, we can also optimize the groundwater management to face the future challenges. Another project in the coastal area, also involved with Henning and Tobias, about sluice and pumping stations monitoring. For the project at the coast that I've mentioned before, I said we want to improve the water management to face future challenges. That project is one step before. So the expertise of the people working there is done now only based on water levels. So we see, okay, the water level of the sea, the water level of the inland, when can I run my pumps and when not? But we have no idea about the discharge volume that we have there, so about the current water amounts. And here we installed measurement devices to quantify the water amounts for the first time, to analyze the water flows. When I'm talking about measurement devices, I'm not talking about single divers for 200 euros. We have here an ultrasonic measurement device with a height of 5 meters to quantify these water flows. So this is these are really big water amounts that we can quantify here. The outcome then would be to have data to optimize the water management in the coastal areas. The last project that I want to show here is, because we were talking also about alternative data, is the DO-IT project, digitization of analog records in time. This is a citizen science project. So citizen science means you have people who want to support scientific activities. These are citizen scientists, and they do not have necessarily a scientific background, but they want to support science, and hence, if you want to involve them, you have to break down the tasks that you have to very simple actions so that the citizen science can work for you. And in that case, we have here a very active level. So the issue that we have is we have a lot of analog data in our archives, like decades of water levels or water flows, and we cannot use this data for simulations. because it's still in its analog way. And here in that project, we developed a website that just went online 1 month before, an API and database behind, and institutes can provide us their scans of the analog data. Citizen science will digitize it, always in very small steps, like for example, here only daily values for 1 month in a year. So we just have to enter like 30 values, or for a week like 7 values, then submit it and build on this numerous activities. We then build the data set. The final data set will be published. We have different data quality routines that ensure that the data set is also useful for the application, and this is a QR code so that you can access this homepage. And if you have, for example, data in your archives that you want to digitize, you can just come to us and we will see if that is a possibility to include it on the homepage as well. This was the last project that I wanted to show, and I would go to that second chapter, to chapter B, but if there are any questions in between to the projects, you have now the time to ask. Okay, then let's move on to the scientific part, precipitation information extension, first in time, in space and time, and in space only. And it's more or less also a summary of the activities that I have done within the last years. And I want to say that all these research would not have been possible without my colleagues, without my former colleagues, and also with friends. And some of them who contributed to this, to the results shown in that talk, are shown here. Maybe you know some of them, maybe you will get known to some of them. And I want to start with the precipitation information extension in time. So why do we need information extension in time? And this is shown here now for whole Germany. Shown here are 2 different networks, and this is all the data that you can obtain from the German Weather Service. So we have here a network with these blue circles. These are daily weather stations. So here I get time series with daily values. Time series here are very long, 50 years or longer. I have a very high network density, but the temporal resolution of these time series is way too coarse for our applications. So I cannot use them as input for the rainfall runoff models or for urban hydrology, because I cannot cope with the dynamics of the hydrological processes. On the other hand, I have this orange network here. I have time series with resolutions of 5 minutes, 10 minutes, or hourly values. This is exactly the temporal resolution that I need. Unfortunately, these time series are very short. In Germany, most often shorter than 20 years, and the network density is way lower. So and the idea of this information extension now is to use information of the time series with the final resolution to disaggregate the time series of the daily rain gauges, and the result would be a network with very high density, with long time series, and with the temporal resolution that I need for my applications. The rainfall generator that I'm using in my applications is a microcanonical cascade model. It's based on fractal theory. And one great advantage of this model is that I have an exact conservation of the daily rainfall amounts. That means if I have a daily time series and I want to disaggregate that one into 5-minute time steps or hourly time steps, and when I aggregate it back to the daily values, it's exactly the time series that I have used as starting point for my disaggregation. The general scheme is shown here. I'm starting with a coarse time step. In our case here now it would be 24 hours, so daily values. I disaggregate it into B finer time steps. B is free, so I have 8-hour time steps. And then for the rest of the disaggregation, B equals 2. So that means I'm reaching 4 hours, 2 hours, 1 hour, and then 7.5 minutes, when I have here uniform transformation to achieve 5-minute temporal resolution, which is the typical input resolution for urban hydrological models. The way that the rainfall could be split here is either the rainfall goes completely into the first final time step, completely into the second final time step, or I distribute it on both final time steps, and therefore I also need a distribution function that tells me how big is the probability that a certain amount of rainfall goes within the first of these 2 final time steps. the second great advantage of that model is that these parameters, so they are also estimated in dependence of position classes and volume classes, but thank you. I don't want to go into detail here in that talk, but the great advantage of that model is that these parameters do not need to be calibrated. They are just estimated in a data-driven way from observations. That means, for example, if I have a time series with 10 years length, I just run this cascade model scheme backwards. So I aggregate it when I count these different splittings, and based on this count, I can then derive the probabilities, and voila, these are my parameters. I don't need to calibrate it, which makes it super effective. Yes, so this is the model that I use, and there are some further developments of that model, and I just want to provide here some ideas or some references where you should have a look first at if you want to apply the model for that application. So if you want to disaggregate daily totals to hourly values, we have a reference here, Journal of Hydrologic Engineering. If you want to go down to 5 minutes, we have another reference. If you want to, or if for the application that you want to intend, the autocorrelation is important. There's a paper on how to improve that autocorrelation. So this is a general disadvantage, that autocorrelation is underestimated in the disaggregated time series. For our applications, this was never an issue, but we wanted to improve it, and here are some suggestions based on different parameters and also on optimization algorithm based on simulated annealing. The last reference that I want to point at is the one by my former PhD student, Niklas Ebers, with the introduction of temperature dependency. And for that, I have an additional slide, because this is something that we need for the future. The motivation for that was we are facing with climate change, we are facing with different temperatures that will affect rainfall and also the rainfall extreme values. And often this climate model data is also only provided on a daily basis. So we wanted to disaggregate this data as well and to have it in a physical plausible way. We came up with the idea to introduce temperature dependency, because you know there's a linear scaling based on the Clausius-Clapeyron and some other effects, and we came up with a very simple strategy just to estimate the parameters within different temperature classes of the day, and that works quite well. So we have proven that with a very long time series in Germany for Bochum with more than 70 years. And what I want to show here are the effects of this temperature dependency. So we have used here 45 stations over all Germany, and the results that I want to show is for these 45 stations. I will show results for the near-term future, 21 to 2050, and the long-term future, 71 to 2100. And always in comparison to the control period, so to the results that we had for the 20th century. Results are also differentiated into the RCP 4.5, so a moderate climate change, and the 8.5 as a worst case climate change. And within these box plots, you find additionally do these 45 stations always combinations of 12 combinations of global climate models and regional climate models. So what can we see here? For the near-term future, temperature will increase around 1.5 degrees for both scenarios. For the long-term future, we have a huge difference. We have 2 degrees Celsius for the 4.5 scenario and 3.5 or almost 4 for the 8.5 scenario. And that translates directly into the rainfall extreme values. So we disaggregated all the daily climate model data that we had for these stations down to 5 minutes, run some extreme value statistics, and the results are shown here for extreme values with duration 1 hour, return period of 10 years. And you can see for the near-term future, we have for both scenarios an increase of around 8 or 9% in comparison to the control period. For the long-term future, it remains identical for the 4.5 scenario, but for the 8.5, we have an increase here of around 20% of the extreme values, which is something that you have to cope with in urban hydrology. The question that we had here for ourselves is how big is the effect of the temperature dependency, and this is shown here in that table. We have the results shown now here for Again, duration 1 hour, return periods of 2 years and 10 years. With the temperature dependency, we have this increase of 21% and 22%. But without the temperature dependency, we would underestimate it. We would have only 12% increase and 13% increase. So the main conclusion is we have to take into account this temperature dependency for the disaggregation of the data. On the next slide, I want to show some possible applications. So the disaggregation of rainfall data makes fun, but it makes much more fun if you can use the data afterwards also for some applications. So the classical way is to use the disaggregated data as input for rainfall runoff models. So you can disaggregate point rainfall data, you can disaggregate aerial rainfall data. This is something that we have done here also for Switzerland. So we applied the model also for different countries, and it works quite well. You can disaggregate it down to 5 minutes. So you can use it for urban hydrological applications. So on the one hand, for the floodings of the manholes within the city, but also for the CSOs, so for the combined sewer overflow volumes. Means when your water treatment plant is full, the water has to be released into the receiving water, and these CSOs can be estimated, and based on these CSOs, you can also estimate infection risks. So this is what we have done for a study here in Austria. We also disaggregated climate model data 2023, so without the temperature dependency, unfortunately. We could estimate the CSOs here from the wastewater treatment plant. We used the disaggregated data also as input for rainfall runoff model for the HPV of the upstream catchment. So we were able to estimate the dilution here, and since the river is used for recreation, we can estimate here the infection risk and how this infection risk will change in the future. So this was a very, very interdisciplinary study, and it was nice to see all the different views on the hydrological aspects from the microbiologists, hydrologists, and climatologists. You can also use the disaggregated time series for statistical analysis. So if you're interested, for example, in erosion, maybe you want to use to estimate the erosivity factor for the Russell equation or for the Ussel equation. And in that publication that was done here for Slovenia, we compared our cascade model with another rainfall generator and some other methods that you can use for this erosivity factor. So the main idea of this slide is the time series are not intended for only one application. There is really a wide variety for possible applications, and maybe you find yourself in one of these applications, and this could be a start for upcoming projects. This was the extension in time only, and I want to come now to the second part, extension in space and time. And here it becomes maybe much more interesting, because this is exactly what we want to do in our project together with UNAM. We want to work with reanalysis products. So for many regions or countries in the world, you have a limited number of data, and one possibility to solve this data scarcity issue is to use reanalysis products. That means you're using all the data that you have all over the world, from every kind, so classical rain gauges, radar data, weather balloons, satellite data, data from ships and planes, and you use these as input for global atmospheric models. The output then would be a numerical simulation over several decades of all atmospheric variables for all parts of the world. And we are interested always in precipitation, and for Mexico, because we are also focusing on hurricanes, we will analyze the variables wind speed and pressure as well. Just to give you an idea what these reanalysis products are, here the maybe most promising for the Mexico project is the RF5 land data. It has a spatial resolution of 9 by 9 square kilometers, temporal resolution of 1 hour, is available from 1950s on until now, so until the last year for now, which means that if you go to a catchment where you have no rainfall data at all and you have to make some studies also as an engineering office, you can just download the data and voila, you have like 75 years of data that you can use for your rainfall runoff models, which is a big gain. When you're in Europe, you could also use the Cosmo 6, which is even finer in its resolution, so 6 by 6 square kilometers here. Unfortunately, shorter period, and it stopped in 2018. So here you have only like 20 years of data. For the Mexico project, maybe we check also second product is a Japanese product with the NSIP data, but this depends a bit on the time and the progress that we have with the first product. So since this reanalysis data is modeled for the whole world, you always have really to take care for your study region to validate it if it's really suitable for your applications. And I want to show here results for a case study that we had in Slovenia a few years before. We had here, so Slovenia is in the south-central of Europe. We had 20 catchments here, mesoscale catchments and reference data, either rain gauges or a merged product from radar and gauge data. So what you can see here in the plots now is you find on the x-axis the values of the observations, on the y-axis the values from the reanalysis products, and here shown wet spell amount and average intensity. And if we focus on that right plot, you see that the two reanalysis products that we have studied were the Era 5 land and the Cosmo 6, they are underestimating the observed values. So if we would have a perfect fit, we would be here somewhere on that dashed line, but we are underestimating the observations. And in general, you would say, okay, this data does not look good, it looks not promising. I won't use the data, I will just take a different data set. But unfortunately, in most cases, you don't have a different data set. So you want to get the most out of that data set that you have here. And we came up with the idea to use the time series from this reanalysis products for the parameter estimation of the disaggregation model that I have just shown before. And what should we disaggregate? Again, we disaggregate daily observations because those we have for very long periods and for high spatial dense networks. And this is the result. This is exactly the same plot. And now we focus on these field markers. So before we had Era 5 land, for example, here the red empty markers. If we use it directly, if we use this disaggregation approach, we have now these field markers, and you can see that we are here close to a perfect fit. We underestimate a little bit the higher intensities for these catchments, but for the Cosmo 6, for example, this is the yellow reanalysis product, the empty markers underestimated here over all intensities. After the disaggregation approach, we have here maybe a very good fit for the average intensity. We have also improvements for the wet spell amount and other variables that I do not show here. But yeah, so we have here a big improvement from this disaggregation process. Also, we are always interested in extreme values. This is shown here now as probability plots. You have the return periods on the x-axis, the quantity on the y-axis, the observations are shown in black. And they are limited from a statistical level to this black dashed line here because the observation period is really short. So we only have 5 years of observed data. So this is the main motivation to use reanalysis data because we don't have these observations. And now the reanalysis products, if we use them directly, these are the dashed lines, we underestimate the extreme values here. So if we use the disaggregation approach, we have then this, the solid lines, yellow and red solid lines, and you can see here that we have now a much better representation of these extreme values. So it is possible to use the data, but you have to be careful. You first have to validate it and then maybe to correct it. And this disaggregation could be one approach that we also want to test in our Mexican project. Nevertheless, here also one example, because we used the data before the improvement also as input for rainfall runoff modelings, here with the GR4H, which is a French model extended with a CMINH, which is a snow module developed by our Slovenian partners. And what you can see here now is the 12 catchments on the y-axis, different data combinations on the x-axis, and these colors here are always the Klingupta efficiencies from the modeling approach. Klingupta efficiencies, similar to the Nash-Sutcliffe efficiency, if it's below 0, you can forget about it. The upper limit is 1, and the closer you get to 1, the better it is. So everything which is shown here as green is quite good. Now let's check these different data configurations here. Data configuration 1 is purely observation. So we have the rainfall and temperature data from the observations. And you can see that we have no red values here. That means the rainfall runoff model works for all of the catchment. Nevertheless, we also do not have perfect values for each of the catchments. For some of them, we only have yellow values. Now let's check 2 more data combinations. We will check data combination 6, which is purely Area 5 land data, and combination 7, which is purely Cosmorea 6 data. And you can see, these are the lines here. You can see that for both of these data combinations, we have always 2 catchments that do not work. Here we have red values. That is how it is. We have to live with that. But for the other catchments, we have yellow and also very green results, which means we have here the possibility also for this unobserved catchments to use the reanalysis directly as input. For the sake of completeness, I should say that the GR4H was also recalibrated for this reanalysis products. However, also to say this was before the correction. So if we correct the reanalysis products in before, the results here would look also much better. So now I come to the last point, the extension information in space only. And in space, I want to talk about areal reduction factors and another citizen science approach. Let's start with these areal reduction factors. So areal reduction factors are limited to extreme values only. And the idea is it's very easy if you have a time series of a rain gauge to run some extreme value analysis for the time series, have an extreme value. But then often you have the case that you want to run a rainfall runoff model with it. And if you have an extent of 20 square kilometers or 300 square kilometers, you will overestimate the runoff if you assume a uniform distribution of this extreme value. So you have reduced it with the catchment size. This is what this areal reduction factor is about. So the general method is you regionalize first all the observations that you have to have spatial impressions of the time series. When you run for each of these point extreme value statistics, this is shown here as an example now for whole Austria. I was here during an internship. And you can see that you have different rainfall intensities in this region. Afterwards, you say, okay, you want to move away from this point-based approach. You introduce this rasters, and this raster size is increasing. So again, you're regionalizing all the rainfall time series that you have as input on the different raster sizes when you run this extreme value statistic for each of these increasing rasters. And these are when the extreme values for your for the different areas, divide them by the extreme values for the point, and this is your areal reduction factor. That one looks in general like that. You have here on the x-axis the space that you want to consider, the ARF on the y-axis, and the result is shown here for some extreme values, return period of 10 years and different durations. And now it's interesting to discuss these different lines. Let's start with this 1 hour line, the black one. This 1 hour extreme values often result from convective events. That means you have an event with a very high intensity, but with a small spatial extent. So if you're going to larger areas, you have to reduce it in space. That means here, for example, for 20 square kilometers, you have to multiply the extreme value by 0.9, and then this is a good estimate for that areal extreme value. If you go to a duration of 24 hours, these extreme values often come from stratiform events. So lower intensity, but very large in space, and hence the reduction in space is way lower. We are here still for 500 kilometers with values above 0.9. What you should always take into account if you have this information, that although we have here a single value, that one is still distributed in space. So this is only a mean value, but here we have the spatial distribution over whole Austria of that single factor. So you can, for example, identify here certain regions that have maybe large differences to the overall value of that ARF. So what do I want to say? Everything that I have shown here on that slide is not new. This is well known. Areal reduction factors depend on the size, on the return period, and on the season, and on the duration. It is not often done on the very large national scale, but what we are trying to do now, where we want to go, is we want to go to the sub-hourly scale. And the issue here is that we do not have too much data of that, but we found here one network. This is the Wegener net, located in Styria in the south of Austria. So very small spatial extent, but hundreds of stations very close to each other. We have, or my former student, Yannick Albers, has used this to determine the ARFs exactly the way that I have shown before. And what you can see here now for the first time, this is still unpublished, ARFs for 5-minute values. And you can see that even for 81 square kilometers, you have here already values of 0.6. So if you're going for urban hydrology, you will be very thankful for these ARF values. Unfortunately, we had to stop here with this 81 square kilometers because the extent of the network, that was not too big, but we wanted to have here a larger scale. This is why another student of mine, Franka Meyer, redid this study now for whole Germany. These are the radar measurements that we have for Germany, so 16 C-band radars, exact the same study, exact the same plots, and so the former plot stops around 80, which is here, and now we go onto 2,600 square kilometers. And what you can see here is that the behavior of the sub-hourly scale, these lines change. So the reduction in space is not that large as it was in before, and the reason is that for this larger spatial extent, the convective events do not play any role anymore for the extreme values. These extreme values that we have here for that extent also come from stratiform events. So, I want to end with the ARFs. Last thing I want to talk about is citizen science. So I've described before what citizen science is about, and this was on a very active level with this digitization process. Now we come to a more passive level. Citizen science, at least in Germany, people love private weather stations because they want to know, oh, how warm is it in my garden? Is it raining? Do I have to irrigate this evening, or is there no necessity for that? And there are a couple of private weather stations in Brunswick, so our city. In comparison to that, we only have one station from the German Weather Service, which is here in the west. We got some additional stations here from the SEBS. This is the municipal wastewater management system that we have in Brunswick. And we had now one really large event in June 2023, one of the largest event within the last decades. And the event went from the southwest here to the northwest here, and it did not hit the station from the German Weather Service. So let's see how the results for that look. First of all, you have here the different rainfall intensities, and now we consider only the station from the German Weather Service. And for this 24 hours for that event, we have here for each of these pixels the highest 10-minute rainfall intensity. Since we only have one station, it's spatial uniform, and you can see here we have rainfall intensities of around 10 millimeters. We also have radar data. Unfortunately, the radar data in Germany is, we trust it in in its spatial distribution, but not in its absolute heights. This is why we correct it with the rain gauges. So with the values of the rain gauges. Since the rain gauge was not getting the information from the event, the radar data got corrected as well to very low intensities, still here around 10 millimeters. If we check now the values of the SEBS stations, we see that we can now see the event for the first time. We have intensities here up to 40 millimeters, and we see the spatial distribution of the event. Now, if we consider only the citizen science stations, we can see that we did not get the main information with this 40 millimeters, but we do see that there was something going on. So if we would just have observed the runoff, we can see, okay, there was an extreme event, and we can see that how the event moved if we check that one over time. It becomes interesting if we have a look at the statistics. So this is a plot here with a lot of information, but I will guide you through the two main points that I want you to show. First of all, we have here shown in different colors the return period for the single spots that we have in the catchment. And the lighter it becomes, the higher the return period is. So we have here spots with return periods larger than 100 years. So first one, the DVD station, German Weather Service. This upper line here is always for the whole catchment, the return period. You can see that for the lower return periods, we have, for the lower durations here, 5 and 10 minutes, we have return periods of around 1 or 2 years. So not a big event at all. And even for the daily extreme value, we have here a return period of 30 years. If we say, okay, we are not taking the German Weather Service station solely, we take all stations interpolated here with an ordinary kriging, then you can see that we have here much lighter values, and we have here for the whole catchment a return period of around 100 years. Now, what I want to point at is this plot. This is the plot that we result only from the citizen science stations. So in comparison to that plot that we have on the very right, you can see that we have some differences, but we have here already a very good estimation without using our own stations. So we have not what we consider here as truth. We are a bit off, but we are way closer when we this approach with the German Weather Service only. So using citizen science stations can help to improve the spatial resolution of these events. But of course, you have to be careful with these stations, and we need a proper data quality management in before. So this was my last slide. Just want to say gracias por su atención. And again, thanks to my colleagues who contributed here. And these are the social media channels where you can follow our institute or myself. Thank you.
For your very interesting talks.
Hola. Thank you, James, for your very interesting talk. Now, ahora pasamos a la sección de preguntas y respuestas. Si alguien tiene una pregunta.
Very good.
First of all, it was really interesting, all the stuff you have been investigating. I'm a PhD student. I have my PhD, it's about all these themes. So I have some quick questions, just fast questions. The first of all is that, well, Mexico is a bigger country it's bigger than Germany, right? And we have daily records all around the country. And the network, the precipitation network of these daily records, it's so long. But we do not have this better resolution as in Germany, as you have like the orange
Yeah.
gauge stations. We have fewer, and these fewer stations are about just 2,000 all around the country. And in the pluviograph, the gauge stations for daily rainfall are over 5,000. Well, the records are still more than 50 years for the daily rainfall data, and for the more resolution, well, for the lower resolution, it's about 10 years old. Can we still use your rainfall model of to get the shape of the histogram as you do?
Sure. So your question is the network density with the final resolution is not so dense as in Germany, and if you can still use it.
Yeah.
Yes. So you can use it. You should always take care of. So what we did in all of that studies, we were always taking the closest station. So the closest high resolution rainfall station for the parameter estimation of the disaggregation. So we have seen. We tried some analysis increasing the distance, so taking not the closest station, the closest but second station, closest but third station, and so on. And with that, the rainfall characteristics were getting worse and worse because the rainfall information was a bit far away, but it still works. But with increasing distances, you just should make sure that you take the rainfall time series or the station selection, maybe based on a cluster analysis, so that you have a hydrologic similar region. So for the rainfall, so not that you have your daily station one side of the mountain and the closest recording station is on the other side, so you have a Louvelet effect, then maybe taking one that is even farther away but still on that side, something like that. Yeah.
Okay, thank you so much. Well, my other question is about the FRA, the reduction areal factor.
Yeah.
As you say, it depends on the variation of the duration of the storm, right? And when you want to design new infrastructure, you have to analyze maximums. And have you already find if there's a correlation between the areal factor and the return period, as you find it for the duration?
Yeah. So the slide that I have shown here is always for one return period. So this is for 1 year. If I would have a look at it for 2 years or 10 years, it would look different.
And is it increasing or decreasing as the return period are different?
Let's have a look at the other one. So this is now, what is the temporal resolution? Here for that 1 hour. So this is for 10 years. For the 1 hour resolution, the higher the return period is, the more extreme is this convective event. Yeah. The more extreme the convective event is, also the smaller is its spatial extension. That means for higher return periods, the ARF value itself reduces.
Yeah, I get it.
It reduces more in comparison to the 24-hour value.
Yeah, I get it. But here in Mexico, we cannot do that because we do not have this resolution data. So we are analyzing the ARF factor with daily data, with 24-hour daily data. But we have been investigating if this correlated. What we have been seeing is that it is increasing as the return period is increasing too. So but it's a question if in Germany you are finding like the same for the return period, not for the duration. Well, this is like the duration between 1 hour and 24 hours. But if you are taking just the 24 hours, like the upper line you have over here, just comparing, but with the return period.
It's a good question. At the same time, it's a super detailed question. We would have to look at the data. So what we always try, we try to provide the whole tables of the ARFs. So also for different return periods and for 24 hours. I would look into that, but I'm not sure if the ARF is increasing with the return period. I would guess it's the other way around, but you have different effects here also because you're closer to the sea. Maybe you have other. Don't worry. Maybe you have other impacts, so more based on the circulation pattern that affects the extreme values. Not sure about, but this is something that we can look into detail. It's interesting. So what maybe when you have these ARFs here, you see they are always below 1. If you analyze them extreme event for extreme event for extreme event, sometimes you have your station value here when the extreme event is a little bit far off, and you will see the higher extreme rainfall intensity for the larger domain. So it also depends on how you apply the ARF. So if it's storm-centered or not geographically fixed. So I'm talking here only about geographically fixed ARF values.
Okay.
But this is something we can discuss later, or would be heavy.
Thank you so much.
Welcome.
Anyone else?
Questions about curiosity. How easy is the interaction with citizens about shared data? Because I don't know, I don't have a lot of experience, but also I collaborate in some projects that especially shared data is not exactly easy if you talk about people that are not involved in the scientific community. So my question is it easy to get access to the data with citizens or with another people that are not collaborate with scientists?
It's a good question, and always depends on the project that you have. So in that case, these private weather stations, during the setup, they can volunteer for providing that data for the network. So there's it's called wundermap.org, or I don't know if this is still the current website, but where you can obtain all the data from the weather station. So in that case, it's quite easy. For the other projects, so with this digitization, you have to actively communicate to the citizen scientists to awake the interest for the project. So what we will try now, we have, so this is very fresh, so we have now this homepage, and now we have the THW, the technical supporting, what is the English word for THW? Okay, we have some groups that we activate for if we have any extreme event or disaster management that supports us with techniques, and they will also promote the app on the homepage afterwards. And most often, when you provide a data set from a certain region, so when you're from Mexico City and say, okay, we could have a lot of more data if you support us here, and maybe sharing the time during your train ride every day for one digitization, and instead of the doom scrolling of Instagram or whatever, maybe you can convince at least one or two, and if that one does it maybe once or twice a week during the year, it's already a lot of additional information.
Thank you so much.
Anyone else? We got a question from online viewers. I'm going to read it. Professor Müller, thank you for your talk of your current research projects. I could venture to ask you a question regarding a groundwater flow that could be considered a source of salinity to a river. We are currently working in a project for the IBWC, International Boundary Water Commission, between the USA and Mexico, collaborating with the University of Texas, that could be estimated salinization of the lower Rio Grande or Rio Bravo river basin. The data seems to show that the most significant contribution to the salinization is due to the irrigation system in that important agriculture area. But there is a doubt regarding the contribution of the groundwater flow during the wet season, for example, rainfall. What is your opinion regarding the this source of salinity?
Good question. The salinity. So there are two things. This question was very long, so I'm not sure if I understood it correctly. One issue, if you take too much groundwater for the irrigation processes and you are close to the sea, then the salinity increases from the water pressure from the coastal areas. If this is the idea behind this question, we don't have this problem in Germany as far as I know, but we have our groundwater expert is also, no, we don't have that problem, no experience with that, but our one of our federal agencies, the BGR, is working on groundwater management systems on islands where you have that problem especially. So maybe we could find some kind of interaction or results from their side.
Okay.
If that was the question. Not sure.
Okay.
It was. Maybe you don't want to read it again.
Anyone else?
Just a quick question. I got lost when you were talking about the micro canonical cascade model. So you're using the historical data with high resolution, temporal resolution, to reconstruct the. You have the different scales, right?
Yes.
30 minutes, 15 minutes, 7 minutes, 5 minutes, etc. Yes. So the question is, you mentioned that you're using fractal structures, meaning that it self-repeats, or you are getting that structure from the historical data. So how do you define that the composition in time is a fractal structure, or is from what you observe in the, in the real storms with low resolution? And you
both.
See what both. So
this fractal theory is the base theory for this cascade models itself. So actually, it was used in turbulence theory for the disaggregation in space with some eddy covariances and all that stuff. Here we use it only in time, and there is a similarity of the rainfall distribution in time on the 5-minute scale as you have it on the 10-minute scale. So this is where the fractals come into game. So, and when we use these parameters for the estimation, this is something that where I've said I skipped that over. You have for this parameter estimation, I've shown I cannot click here anymore. I can. So, because it's much easier to show than just talking about it. So I've just said I have 3 different probabilities here that 0, 1, 1, 0 and x1 minus x splitting, so that the rainfall goes into the first final time step, the second one, or this distribution. And I said these parameters are estimated and depends of position volume classes. So what does that mean? That means if, for example, this here is my time series now, yes, on this 8-hour level. This first wet time step here with this 9 millimeters is at the beginning of a rainfall event, so it's a starting position. So I'm estimating parameters only for starting positions and then also for a lower volume class and an upper volume class. I have different position classes. I have also here an enclosed position, ending positions, and I have isolated positions. And these take into account the different behaviors at the beginning and for isolated events. And this is something that you have to consider, because otherwise it would be just kind of randomness. But if you consider these different positions and volume classes, then you can see that the structure really plays a role and can be found again. And what we have done in this current study from Niklas is also we have compared the parameters, and they are this fractal symmetry. So you always have, if you're familiar with the topic, you have this log plots of the m versus the alpha moments, lambda moments. This here is a linear behavior from daily values down to hourly values, but you have a different behavior from the hourly scale down to the 5-minute scale. So we are estimating one parameter set from 5 minutes to 1 hour, and another parameter set from the 1 hour to the daily values. And then from daily to monthly, it's again a different parameter set. So it's not it's not universal fractal in that kind that you can just upscale the 5 minutes down to annual values. That does not work because on annual values, every time step is wet and it's more homogeneous. So it always depends on microclimate, climate, and then above the daily values, you have the circulation patterns that come into game.
Thank you.
How many storms did you use to calibrate this cascade model?
This is not calibrated with storms, it's calibrated with continuous time series. And what we have as a selection criteria for Germany, I took only stations with a minimum length of 7 years.
7 years, continuous 7 years with this time duration of 3 minutes. That's
5
what
minutes.
I understand.
Yes.
Yeah?
5 minutes.
5 minutes and 5 minutes, and you have a record of 7 years long, right?
Yes.
Okay. Thank you so much.
Yeah, you can also use, so we have checked the impact of the disaggregate, of the rainfall statistics of the disaggregated time series, the fluctuation, and it's becoming less for 7 or 8 years. And of course, it becomes even more less if you would use 20 years, but we said as a trade-off between the number of stations available and the fluctuation, the statistical range that you have from the data, we said 7 or 8 years is fine for us. If you would have only 5 years data, I still would use the data. So better to have 100 stations with 5 years of data in comparison to have 10 stations with 8 years. So it really depends on your situation.
Bueno, con eso terminamos la ronda de preguntas y respuestas. Muchísimas gracias por tu asistencia. Thank you, Hannes. Welcome to UNAM. Welcome to Mexico, all of you. Thanks again. Y les damos un aplauso, por favor. Gracias por su asistencia. Hasta la próxima.
Bueno, queremos dar el aviso de que van a proporcionar un código para una encuesta a los asistentes para, bueno, su opinión sobre este evento y también para, que puedan comentar el tipo de eventos que podrían ser de su interés. Entonces se va a dar un código QR que está afuera para que por favor nos puedan apoyar con la encuesta al Departamento de Cómputo. También, bueno, vamos a otorgarle su reconocimiento al doctor Hannes. Nuevamente agradecerle por su muy interesante presentación y con bastante contenido que puede dar ideas también para nuevas, también aquí líneas de investigación para los estudiantes que estén interesados ya en sus doctorados, también en temas de su maestría. Y pues muchísimas gracias por su atención. Y pues sería todo. Muchísimas gracias. Buena tarde a todos. Sí. Bueno, también están para su equipo de trabajo, también se les está otorgando sus recuerdos del Instituto de Ingeniería. Muchísimas gracias. Bueno, y tienen su tacita por si quieren para las máquinas.
Thank you. Thank you very much.